Good morning. Let's start the first lecture today. Okay, the speaker is James Newton. He will talk about automorphic liftings.
All right, thanks very much. So in the last two lectures, we saw both the kind of automorphic side and the Galois deformation theory side of the Taylor-Wiles method about what happens when we allow ramification at auxiliary primes. And today I'm going to put those together and explain how you can use those ideas to prove, well, something like R equals T, or at least show that this map from R to T has maybe a nilpotent kernel, or maybe something a little bit weaker than that. But we'll see later some precise statements. But the goal will be to show that our map from a Galois deformation ring to a Hecke algebra has nilpotent kernel. I realized we didn't really give sort of specific references, so I thought I'd correct that this morning. So basically, the ideas we're explaining are contained in Caligari-Geraghty's paper, which has Beyond the Taylor-Wiles method somewhere in its title. There's also a nice series of lecture notes. Well, is it a series of lecture notes? There's one document by Jack Thorne, expository on this, which is also very nice. Again, Beyond Taylor-Wiles are the keywords you can look for in the title. And as I sort of mentioned earlier, in how we're presenting things, because we just want to explain the sort of key idea in this Caligari-Geraghty paper, we're assuming a bunch of conjectural statements, like about the vanishing of cohomology, or about association of Galois representations to automorphic forms. If you want to see some precise unconditional statements in this positive Taylor-Wiles defect situation, then a good place to look is the 10 author paper. Here are the initials of the authors. All right. Okay, so let me get to it. So I'll recall a bit of our setup. So we've got our Hecke algebra T, which we defined as a subalgebra of endomorphisms of a complex computing cohomology of a locally symmetric space. Okay, and we've localized a non-Eisenstein maximal ideal M. So we've got our residual Galois representation, rho M bar, which is absolutely irreducible. So that puts is in a good position to do deformation theory for this Galois representation. And then we have some assumptions that sort of showed up in Patrick's talk. We're going to have P greater than N for sort of simplicity, and it simplifies things in a couple of different places. We'll also assume P is unramified in the totally real field, in the number field F that we're interested in. Okay. And then Patrick talked a little bit about looking at Galois representations which are crystalline of Hodge-Tate weights 0 through n-1 at places dividing P. So that crystallinity on the automorphic side is going to correspond to us having a maximal compact level subgroup at places dividing P. So this level subgroup KV will be GLNOV, the V dividing P. Some of the setup. And then, well, this is sort of another conjectural statement, but we sort of almost know how to prove it in many cases. So general is conjectural. I'm going to assume that there is a map from R to T. So by definition of R, that means we can construct a Galois representation with coefficients in T. And yeah, let me mention a little bit about this R. So as in Patrick's talk, this is a global deformation ring. For a residual representation with some local conditions. So we have this crystalline condition corresponding to the level subgroup of places dividing P. We have the Hodge-Tate weights being 0 through n-1, which corresponds to us looking at cohomology with trivial coefficients of our locally symmetric space. So remember, we had cuspal automorphic representations of weight 0 contributing to those cohomology groups, and their associated Gauss representations should have these Hodge-Tate weights. So that's that. And then you remember we have this sort of set of places S where we're allowing some non-trivial level. So V is not in S. Then we have a maximal compact level subgroup. On the Gauss side, that means we'll be able to just assume our Gauss representations are ramified at those primes. Okay. And the places in S, they're going to appear in this sort of R lock that appeared in Patrick's talk, this tensor product of local deformation rings. So for the in S, some of the places in S are places dividing P. So I already took care of those here. I talked about the local deformation condition at places dividing P. The places in S where we don't divide P, the easiest thing to do is just say we won't impose any special local condition. We'll just look at arbitrary local deformations for these places D. So there's going to be an RV which corresponds to a local deformation condition at D. And you can try and choose this deformation condition carefully in a way that sort of matches the level you've used for your cohomology groups. And then you'd have to sort of prove that this map from R to T factors through the right local condition. But yeah, as I said, we'll just maybe take the unrestricted condition for simplicity. So that means RV will be the full local deformation. Okay, let me just add here our other key assumption to make the Taylor-Wiles method work. We have to assume our residual representation has big enough image, because in order to find our Taylor-Wiles primes, we need a regular semi-simple element in the image of a Gauss representation. So that means we assume a restriction of a residual representation to DFC to P. So for us, we're going to assume it has enormous image. One of the consequences of that is that there will be these elements with distinct eigenvalues, regular semi-simple elements, in the image. So that's what will help you to find Taylor-Wiles primes. And I should mention, this is related to something Peter raised at the end of my previous lecture. So you might want to weaken this enormous image criterion, and there's something called adequate image, which does that. And where I was working with the Iwahori Hecker algebra, this works with a certain parahoric Hecker algebra. So this is some sort of weaker notion than an enormous image. And in this positive defect case, this kind of version of the theory has been worked at in a recent paper of Miagkov and Fon. So this adequate image assumption is very close to just asking for this restricted representation to be absolutely irreducible. And that's sort of more or less the limit of what we can do at the moment in terms of looking for these Taylor-Wiles primes. Maybe I should say this sentence here, adequate image also possible. That's how you construct the Taylor-Wiles prime. So remember, a Taylor-Wiles prime was a prime V where the image of Frobenius was a regular semi-simple element. So for sure, we need to have regular semi-simple elements in the image if there's any hope of finding a Taylor-Wiles prime. But then you can use, if you do have regular semi-simple elements in the image, you can use Chebyshev density to find a Taylor-Wells problem. And we're restricting to FZ to P because you also want your primes to be 1 modulo P. Any more questions at this point? Right. So I explained our target theorem is maybe that R to T has nilpotent kernel. Okay. So we just sort of make explicit why that's what we might want. So the corollary of this is that if you have a Gower representation, with coefficients in our p-adic coefficient field, and if that Gower representation sort of comes from a map from R to E, which just means that rho satisfies the various local conditions you've put in place when you define this global deformation ring R, then, well, I've got a surjective map from R to T with nilpotent kernel. So any map to a reduced ring like this field is going to factor through T. And that's good news because maps from T to E are exactly systems of Hecker eigenvalues which appear in the cohomology of our locally symmetric space. So you have to sort of just think about the definition of T to see this, but it's basically, yeah, the way we set up T is that these homomorphisms from T to E are going to correspond to automorphic representations. So let me be a bit more precise. So rho will be isomorphic to rho pi iota for a custom automorphic representation pi. Contributing to the cohomology of my locally symmetric space. All right, and let me just briefly mention a sort of simple reformulation of this statement that R to T has nilpotent kernel, but it'll be useful when you do some sort of commutative algebra. The equivalent thing is that if we look at our cohomology groups, okay, then, well, these cohomology groups, they all have an action of T. So they get an action of R from R to T. So this is an R module. And this map having nilpotent kernel is equivalent to the support of this R module being everything. I mean, the spectrum of R and the notion of support doesn't see this nilpotent kernel. So that's more or less what you do to see this. So this is one way of describing our goal. We just want to show that these cohomology groups have full support in R. No. We don't know. No, maybe not. Yeah, if it's torsion in T, there's no reason why it should be reduced. I mean, something I'm suppressing throughout is that actually when one proves these theorems in positive defect, you have to do stuff up to a sort of error term, which is the nilpotent ideal in T. So in some sense, things will only be working up to the reduction of T anyway. Not if you want local global compatibility as well. Okay. All right, so that's the sort of preamble. And now I'm going to go back to what happens when we allow ramification on auxiliary primes. So I will go to a new board for this. The corollary is a corollary of a target. Sorry, I should have written target theorem. Maybe that would have made sense. But I'm not stating it as a theorem yet. I'm just saying that's our goal. Yeah. Didn't find the erasure. Ah, good, good. Okay, so this is going to be section 1. I'm going to recap what we've done about allowing ramification at Taylor-Wells primes. Okay, so what can we do using what Patrick explained? Well, for each positive integer m, what we're going to do is choose a set of Taylor-Wells primes u sub m such that this set of primes has level m. So that means to be in Qm, the congruence that the cardinality residue field is 1 modulo Ptn. Okay, so that's going to ensure as m gets big, we're allowing sort of more and more p power ramification in our Gauss representations. Okay, and then the crucial condition on the Galois side is that you can choose these Taylor-Wells primes so that a dual Selma group vanishes. So I hope I've got this notation right from Patrick's talk, whether it's H1 sub Qm, because these are going to be cohomology classes which become trivial when you restrict to places in Qm. Coefficients were our residual representation, adjoint representation twisted by 1. Okay. So we had that vanishing, and that gave us some crucial information about a presentation of the global deformation ring over local deformation ring. So I'll recall that information later, but the kind of Galois cohomology statement we needed was vanishing of this dual Selma group. Okay. So that's the crucial thing. And what the other important thing, we've got a set of primes, and we just have to choose enough primes to get this vanishing of the Selma group. And so in particular, the size of this sets of primes is independent of n. So the size of each set of Taylor-Wilks primes is going to be what I call little q, and that's independent of n. I think this was the notation in Patrick's talk. Maybe not.
Yeah, it wasn't the notes I entered, but I think.
Okay, good. I wasn't. SQ perpendicular, beautiful. Okay, so instead we have this Selmer condition at Q, which is going to describe the tangent space of our deformation ring when we allow ramification at Q. And then the dual Selmer group is going to involve the sort of dual Selmer condition. But yeah, explicitly, this is just going to say you look at cohomology classes here, which vanish when you do the local restriction map to places in Q. Is it okay? Great. Okay, so now we have the sort of picture when we allow ramification at one of these sets of Taylor-Wilks primes. So we have our global deformation ring R to start with. Remember this in particular classified reps, which were unramified outside Q. Outside S. So all the representations classified by this deformation ring are unramified outside S. Then one of our sets of Taylor-Wilks primes, Qm, we can look at the deformation ring where we relax that ramification condition and just say that we're unramified outside S union Q. We keep the local condition at places dividing P the same. That's going to be present in both rings. We've just allowed some more ramification of these auxiliary places. So that's the deformation ring picture. And then we have the picture for the Hecker algebras as well. So here we've got the Hecker algebra TQM, which I'll say more about just now. So in lecture 2, I defined this Hecker algebra where you just allowed ramification at one extra prime. So lecture 2. Right at the end, I defined this sort of bigger Hecker algebra where you allow ramification at one place. But you can do the same thing with a set of places. Maybe I'll write down precisely what's happening on the next board. Okay. But this is just going to be exactly the same deal, except now you're allowing, you're sort of shrinking the level at all of the places in Qm. Okay, so let me just give you a definition of this Hecke algebra TQM. So it's giving me an image of an abstract Hecke algebra in the endomorphisms of a complex computing homology of a locally symmetric space. So what we do is we take the spherical Hecke algebras, places away from S like we did before, and also we now avoid the places in our set of Taylor-Wiles primes Q. We have spherical Hecke algebras at V. And then we also wanted just to keep track of this ring of, yes, thank you very much, the not in S union Q. Right, that's where we're going to have spherical Hecke actions. And we also need to keep track of the diamond operators. So now that's going to be a product over, hence product over places in Q then. Okay. There we have the group ring of this group delta V that I introduced in lecture 2. Remember, this is just a product of n copies of cyclic order group of order P to the n. Right, so this is the kind of abstract Hecke algebra. We're going to take the image of this thing in the endomorphisms, it's something in the derived category of modules for this product of group rings. And yeah, let me just put the notation in here and I'll define it next. So we're going to have Cn. Okay, this is going to be something in this derived category. And the point is that I'll think of this as a chain complex and its homology is going to compute the homology of the symmetric space with this sort of adjusted level at places in our set of Taylor-Wiles primes. So away from Q, I'll just write Q for now because M is going to remain fixed for this bit of a discussion. So away from Q, we have the same level as before. At Q, we introduce our little subgroup of the, it's not so little, but anyway, it's a subgroup of the Iwahori group, I primed V. That's the level at places in Q. Okay. And then doing homology with coefficients in O, and we've still done this localization by our non-iso style ideal M, sort of enhanced a bit to keep track of some Hecke operators at places in Q. Q is QM. Yeah, I'm just sort of forgetting M because M's fixed for the moment. That is what's going into M tilde. So you use these UV operators to do this localization, M tilde, and then you can forget about them. At least the way I'm presenting it for now. They've sort of done their job to do this extra localization, and then you can forget. Okay, so that's where the Hecke algebra lives. And yeah, again, like if you're not used to thinking about sort of the objects in the derived category computing cohomology or homology of some manifold, then you can just sort of restrict to this L0 equals 0 situation where we've just got a single homology group in a 1 degree and it's a free O module. So if you want, you can just look at that case, and then all that's happening is we're looking at the image of the Hecke algebra in the endomorphisms of that free O module. Or if you like, the sort of faithful quotient of a Hecke algebra acting on that module. Okay, good. Let me do a little bit more notation just to abbreviate things. So we have this tensor product of group rings, O delta V. So that's, of course, the group ring for the product of the groups. That product of groups I'll call delta QM. Okay, so this group ring O delta QM is acting on TM. Okay, and it's also acting on RM. So that's something that appeared right at the end of Patrick's talk. Hecke algebra RQM, sorry, deformation ring RQM. That's also naturally an O delta QM algebra. And the way this action of O delta QM is defined is by looking at the restriction to inertia of the universal representation. All right. And what else do we know? This O delta QM algebra structure allows us to recover the original deformation ring R from RQM. So if you take Kerr invariance, when you look at what that means for the Gauss representations, you'll see that a homomorphism out of RQM, which factors through this covariant group, will classify a representation that's got trivial restriction to inertia. So this is sort of naturally equal to the deformation ring we started with. So that's how you go back from sort of auxiliary level QM to the level we started. Good. Yeah. TQM maps to T. Yeah, I'll talk about that next. Thanks. Okay. So, and the idea is the following. We're also going to have a map from RQM to TQM. So that means we can construct a Gauss representation with coefficients in this Hecke algebra TQM. And these are both O delta QM algebras. And then a sort of local global compatibility statement at the places in QM tells you that this should be an O delta QM algebra map. So remember, the action of delta QM on RQM is telling us something about the ramification of our Gauss representations. The action of delta QM on TQM are these diamond operators coming from the change in level structure. But the fact that those two kind of actions of delta QM correspond is exactly some kind of thing saying you can describe the ramification in the Gauss representation in a kind of automorphic way. Okay. It's sort of right. It's here just to remember that TQM by definition acts on CM, the homology at level delta QM. So by just composing with this map, we get an action of RQM on CM. Which is good. And when we do this sort of return to level 0, when we take co-invariance for the delta QM action, then what happens, hopefully isn't too surprising, you take co-invariance for the deformation ring, then I said what you get is just the deformation ring we started with. So that's R. That has an action sort of via T on the homology with no auxiliary level. Okay. And we also have a control theorem for the homology when we change the level. So this is basically coming from Hochschild-Serre. So that if we take derived co-invariance, then we return back to our homology at base level because we had this delta QM torser. And this is how you get from homology upstairs to homology downstairs. Okay. And this diagram will commute. That's the idea. So this tensor product will act on this thing just by functoriality. So that's going to be a sort of important picture for us. So we've got this Gauss representation where we allow extra level acting on the homology of a locally symmetric space. And taking co-invariance is going to return us back to the picture at level 0. Yeah, good question. So I do TQM. I take co-invariance of TQM, then I certainly get a map to the original T. And in general, this might not be an isomorphism, but when we come to sort of questions of support, the sort of primes of R in the support of this will be the same as the primes of R in the support of this. So these are not necessarily the same. This is like the difference between taking, you have some endomorphisms of a module. You can look at the image of those endomorphisms in the endomorphisms of the module modulo some ideal, or you can just reduce the algebra of endomorphisms modulo the ideal. So yeah, they're not the same in general, but there is a map, and they're not going to be very far apart. Yeah, thanks. Oh yeah, I was going to comment on that. So thank you. Yeah, so you may well ask, yeah, what happens if I take the derived tensor product for this deformation ring? And that's certainly an interesting thing to do. Then you would get some derived enhancement of R, which acts on C. So this is something that appears in sort of Venkatesh's work on derived deformation theory and thinking about how that derived deformation rings of Gauss representations might act on the cohomology of locally symmetric spaces. Venkatesh. No, not in the L0 greater than 0 situation. That's the whole issue. Yeah. Yeah, that's a very good point. Yeah, you might ask whether RQM is flat over O delta QM. May not make any precise statement. Maybe when L0 equals to 0, you might sort of expect that. what we'll see in positive defect is that these RQMs are not growing as fast as the group ring is growing. So yeah, you don't expect flatness when you're in positive defect. Thanks. More questions? Okay, so I said that we chose these sets of Taylor-Wiles primes QM so that some dual Selma group would vanish. And let me recall the sort of concrete consequence of that, which Patrick gave us. So we chose QM so that a specific ring R infinity, whose spectrum was this cube that we drew a couple of times. That's going to be the ambient space that everything lives inside. So that was a tensor product of local deformation rings when V is in our set S. And then it's a paraseries ring in some variables. Okay. And the way things are set up is that we're trying to present the global deformation ring over the local deformation ring. So that means we have some generators x1 through xg, and that's going to surject onto our deformation ring RQM. Okay. And the sort of application of Poitou-Tate that's crucial to the Taylor-Wiles method tells you that you can take G to be a certain value. So it tells you the dimension of R infinity is 1 plus Qn. Remember, Q is the number of Taylor-Wiles primes. Minus this Taylor-Wiles defect L0. And I should say here that we're sort of, for simplicity, assuming that the V in S are local deformation rings exist, which means we have scalar endomorphisms. For the local residual Garrett notation. The fix to this, it's not too difficult. You just sort of introduce lifting rings at these places instead of deformation rings. I mean, there's a bit of bookkeeping to keep track of that. I mean, I'd say this is super easy, but I was just talking to Toby over breakfast, and it was Kissin who introduced this, along with many other ideas in this area. And when Kissin first did this, it was actually very interesting and surprised people that this could be done. So this introducing the lifting rings or frame deformation rings at these places is a non-trivial idea, but once you've seen it, it's quite straightforward to make it work. Like many things, I suppose. Okay, cool. So why is this dimension of R infinity going to be useful? Well, let's think about what happens on the automorphic side. We have an action of this group ring, O delta QM. And I'll remind you that delta QM is just isomorphic to a cyclic group, V mod P to the MZ, and then a product of it, Q times N times QN. So in delta QM, we're taking a product of Q copies of things. So yeah, this is the group we get here. Okay. So it's by sort of choosing generators for your cyclic groups and choosing an ordering on the Taylor-Wiles primes, what you get is a surjection from a paraseries ring in Qn variables. So I won't need to use the names of the variables, so let me just say Qn variables. And Qn is somehow the sort of relative embedding dimension of this ring. Like if you think about the spectra, this is going to be the sort of smallest formally smooth scheme into which this spectrum will embed. Okay, so this is the sort of best we can do if we want to present this ring as a quotient of the power series ring. So this ring, O with Qn variables, that subjects onto all of these group algebras, is going to be what we call S infinity. And via this projection from S infinity to the group ring, basically we have a lot of S infinity modules and S infinity algebras in our picture now. Everything had an action of one of these O delta QMs, so everything's going to obtain an action of S infinity. Now we have this sort of crucial coincidence between the automorphic and Galois sides. On the Galois cohomology side, we have this computation of the dimension of R infinity, and we got the dimension of S infinity minus L0. Okay, so that's going to be crucial for us. I'll explain that in a moment. Okay, so I've set these things up carefully for this varying positive integer m. Okay. And now the sort of approximate idea is that we're going to take a limit over m. And I put limit in quotes because there are no transition maps between our various pictures as m varies. So there's no inverse system indexed by m. You can't actually take an inverse limit. So traditionally, the sort of fix was to do a fairly kind of delicate compactness kind of argument to show that you could sort of cook up some transition maps using the fact that our picture's kind of finite, at least with you reduced modulo powers of maximal ideals. Peter Scholz gave a very nice sort of reinterpretation of that using an ultra product construction, which I will talk about at the end if I have time. That's my plan. So for now, we're just going to roll with this and assume we can take the limit in some way as m tends to infinity. Let me just mention the sort of crucial thing is that if you look at the kernels of these various surjective maps from S infinity to O delta QM, you intercept them as n varies, then you get just a zero ID. That's something you can check. That means as you do this sort of quotes limit, you'll go away from modules over L delta QM to modules over S infinity. I think Peter likes to say, I heard him say that doing this ultra product construction is like allowing ramification at a Taylor-Wiles prime, which is congruent to 1 modulo p to the infinity. That's kind of what you want to do, to allow loads and loads of ramification, p power ramification. Okay, so I won't go into this limit construction yet, but I'll tell you what happens at the end of the construction. What do you get in the limit? So I'm going to get a ring, which I'll call R patch, which is the limit of my deformation rings RQM. Okay. Now, the very nice thing is that we have control over these deformation rings by R infinity. All of these deformation rings are quotients of R infinity. So when we take this limit, you still get a quotient of R infinity. So that's good. What else happens? Each of these RQMs are O delta QM modules. So in the limit, you still have an S infinity algebra structure in this ring. So there's a O algebra map from S infinity to R patch. Okay. And the RQMs all acted on the homology at level QM. So the limit is going to act on what I'll call C infinity, which is the limit of the CMs. And the other piece of control we have comes from this assumption on vanishing of cohomology. So if you remember, my complex computing homology is going to be quasi-isomorphic to a complex of finite 3 O delta QM modules in a specific range of degrees, Q0 to Q0 plus L0, which comes from this vanishing of mod P cohomology, which is a conjectural analog of kind of vanishing I mentioned due to Borel and Clauzel. Good. So this means as we take the limit, we also have control on C infinity. That's just going to be quasi-isomorphic to a complex of finite 3 S infinity modules in this range. Right. Same thing over S infinity. Okay. And now you could take a sort of limit of the Hecker algebras as well. It's kind of more convenient to think about the Hecker algebra as the image of the Galois deformation ring in the endomorphism algebra of the complex. So let me make a definition that me, the sort of patched Hecker algebra, would be the image patched deformation ring in the endomorphism algebra of the patched complex. Yeah. The R patch is the map from S infinity to R patch. Yeah, right. So there's maps from O delta QM to RQM. So in the limit, this becomes a map from S infinity to R patch. If I was really taking an inverse limit, this would be the inverse limit of these things. And this inverse limit would have an action. It's okay. So this appeared just about at the end of Patrick's lecture. So these maps are given by thinking about the ramification of the Galois representations classified by this deformation ring. Okay, cool. And the final important thing about what we get from this patching is that, as usual, we can return to level 0, right, by taking covariance. So we with tensor product over S infinity with O, where the map here is just to send all the power series variables in S infinity to 0. Then, because if we took covariance for our QM over delta QM, we get R back. In the limit, when you do this tensor product, you're going to get R back as well. And the same deal for the complex, C infinity. And we have compatibility between those two things. Right. So that's what you get out of the patching. Now I'm going to explain how you do a little bit of commutative algebra to leverage this equality of dimensions I've got in the box at the bottom. Here's a proposition, which is the kind of crucial bit of commutative algebra, which makes the Caligari-Garrity version of the Taylor-Wiles method work. So in this situation we have, they prove that C infinity, this patched complex, has non-zero homology in only 1 degree. So actually, it's just a shift of a single module. Chalk. This degree is Q0, the bottom degree, where it can live. So I said cohomology, let me use homology. For convenience. So HQ0 is the non-zero one. And I'll give this cohomology group a name. It's going to be M infinity. Good. And even better, they deduce that M infinity is maximal Cohen-Macaulay over R infinity. So that means the depth and dimension of this module over R infinity are equal to each other and equal to the dimension of R infinity. Mind you, dimension of a module just means dimension of its support. And that's the thing we actually want to prove is big. Support of this module is going to be telling us about Gauss representations which come from automorphic forms. Okay. So this proposition tells us actually that M infinity is pretty big. The dimension of its support is the dimension of R infinity. So that's this cube that we had where everything was living. And this is what says that when we patch, we've actually filled out the whole of this cube. It's finite free over S infinity. Yeah. No, so wait. No, sorry about that. It's not finite free over S infinity. Yeah, we'll see this in a moment. It has projective dimension L0. Yeah. I'll add that to the statements, actually. Thanks very much for the question. Yeah, so what's happened is we've got this complex C infinity living in degrees Q0 to Q0 plus L0. These terms are all finite free S infinity modules. And what this proposition tells us, or the proof will tell us, that this complex is a projective resolution of its smallest degree homology. That's what's happening with the sort of homological algebra part, if you like. Okay, so let me just write down one consequence of this proposition. I mean, I'll just give you the idea of its proof without actually proving it. So a particular consequence so we have a Cohen-Macaulay module. That means its support is equidimensional. It's a basic fact about Cohen-Macaulay modules over local rings. And that's good news because it shows that the support of M infinity, because we're maximal Cohen-Macaulay, the support is a union of irreducible components in spec R infinity. Let me just mention now that this support is the same as the spectrum of our patched Hecke algebra, by definition, basically. So the support of M infinity is support is equidimensional. It has dimension equal to the dimension of R infinity. So all it can be is this union of irreducible components. And that's just from a definition of T-patch, actually, because T-patch was the image of R patch in the endomorphisms of M infinity. Okay, so let me just give you the idea of proof of this proposition. So L0 is the amplitude of my complex. And what that does is that gives you a lower bound on the dimension of its support. So on the dimension of T patch. And that lower bound is going to be exactly, this amplitude will correspond to the codimension of a support. So the lower bound will be dimension of S infinity minus L0. But now, crucially, this is the dimension of R infinity. And we've chosen R infinity so that it gives an upper bound for our whole picture. Everything's embedded in the spectrum of R infinity. So this dimension of R infinity is also an upper bound for the dimension of everything, of R patch, of T patch, etc. So this lower bound actually coincides with the upper bound. This is always what sort of happens in the Taylor-Wiles method. You have a sort of, the patching allows you to show that you have a lower bound on the kind of size of your automorphic locus. That's what this lower bound is. And it coincides with the upper bound coming from the Galois side, the Galois deformation field. So this is what tells us that the dimension of T patch is equal to this. It's equal to the dimension of R infinity. That tells us exactly that we have lots and lots of automorphic forms after we did this patching. So I'll just illustrate this in two examples, one with L0 equals 0, one with L0 equals 1. I should say the proof of this proposition is not like super elaborate. You just have to play around with depth and dimension and the Auslander-Buchsbaum formula. But I think it's maybe better just to illustrate with a couple of small examples. So let me do L0 equals 0. That's a kind of classical case. So that's where our cohomology complex, C infinity, is just going to be a single module in degree Q0. And in this case, the module will be finite free over S infinity. Okay. That's good. So we think about T patch. That lives inside endomorphisms of M infinity. So it just lives inside a matrix algebra over S infinity. This was a S infinity algebra. So in particular, you notice that this map is injective. S infinity injects into T patch. So that's, I mean, it's very simple in this case. That's what tells you that T patch is big. It contains S infinity injects into it. So without doing any more commutative algebra, I can already say, well, T patch is pretty big. So L0 equals 1 next, which is a bit more interesting. just give you a toy model for things might look like in the L0 equals 1 case. So maybe one of the toy features is I'm just going to assume S infinity is a paraseries algebra in one variable. Here, in reality, we have sort of q times n variables. That will never be 1, I think, unless maybe in some particular case you could choose it to be 1. Anyway, it's basically never going to be 1, but let's assume we were actually just over this small ring. L0 is 1, so that means our patch complex just has 2 non-zero finite free terms. And because I'm really doing a toy model, I just want to assume that those 2 non-zero terms are just rank 1 over S infinity. So here's my complex. The homological degrees are Q0 and Q0 plus 1. And there's some map between these things. So this is just multiplication by some element in S infinity. So what do we get here? Well, HQ0 plus 1, if F is non-zero, we're going to get 0, right? This is an integral domain, so the kernel of multiplication by F, if F is non-zero, will vanish. Of course, if F vanishes, then we get full copy of S infinity. Okay. And now the point is, in our setup, this second option is too big. Everything's living over R infinity. There's an R infinity action on here. In this case, we have codimension 1. So this ring has Kroll dimension 1. This module is supposed to be finite over R infinity. Okay. So this second option is impossible, right? This is way too big. This gives us a 2-dimensional thing. There's no way you can be in this situation. So that's why that's where this fact that the dimension of R infinity provides an upper bound, that's where that comes in. If you had F equals 0 here, it would tell you the dimension of T patch was too big. So the fact that R infinity has codimension 1 write this equation again. Dimension of R infinity is the dimension of S infinity minus 1. That's what rules out this position, this option. So F is non-zero, and that tells us that the HQ0 plus 1 vanishes. So we are just concentrated in 1 degree. So that's a very, very simple example, but I think it does really capture the essence of this Caligari-Geraghty proposition. So an interesting thing to do if you've got time is just to think about what this is saying about torsion in cohomology as well. You think about torsion. So P torsion. The fact that R infinity is P torsion free, and the fact that the degree Q0 homology is supposed to be maximal Cohen-Macaulay over R infinity, that will tell you that actually the homology here will be P torsion free. So even if we had lots of torsion before patching, at least if you assume enough things, you can see that after patching, you'll end up with P torsion free things. Okay. Right, so that's the kind of commutative algebra part of this story. Some aspects of it, at least. Any questions at this point? All right. Let me just sort of unravel what this says about Galois representations. Write down a theorem, which I'll say it's immediate from a proposition. It's sort of immediate if you've had some experience with these things. Assuming it's true. I think it's true. Okay. Theorem is going to say we've got two Galois representations. So we've got rho p-adic Galois representation. Then we've got another p-adic Galois representation, which we know is automorphic. So we're going to have a rho pi iota. And we're going to assume that this first representation, it comes from R, our global deformation ring. So it satisfies the right local conditions, and it has the right residual representation. And rho pi iota, we're assuming it's also coming from R, but even more, it's automorphic. So we can assume this one comes from a map from TT. So in other words, this pi is a cross-product automorphic representation, which contributes to the cohomology groups we've been looking at. Okay. And then an automorphy lifting theorem is going to tell us, the idea is that we want to say, well, look, rho pi iota is automorphic, and it has the same residual representation as rho. Okay, so we want to deduce that rho is automorphic. That's always going to be the statement of an automorphy lifting theorem. And we can now do that with a little extra assumption. So we have to suppose something about irreducible components of local deformation rings. So that's coming exactly from this consequence about the support of M infinity being a union of irreducible components in R infinity. So we're going to suppose that rho V in S that our local representations lie on a common irreducible component of the local deformation ring. Let me say that also they're not, we want to assume they're not sort of an intersection point of irreducible components. So let's say they lie on a unique irreducible component, and it's the same one in both cases. The same unique irreducible component. In other words, I'm going to say that they only lie on this irreducible component. Yes. So that's our local defamation ring for all V in S. Yeah. Yeah. So for simplicity, I set things up so that RV was the unrestricted defamation ring. There's some flexibility here. You could choose some different local condition, and then maybe you would have fewer irreducible components, and you might sort of know this condition in advance. Probably, yeah. Yeah, I'm trying to do that in my head and I'm failing, but yeah. I just mean I'm saying that each of these representations should only lie on one irreducible component. They don't lie at a crossing point. Yeah, it's just rho pi iota. You're right. But let me not write this. So the idea is we'll go to this patch situation and we'll say that rho pi iota, because it's automorphic, gives us a point in the support of M infinity. Okay. So that means the unique irreducible component passing through rho pi iota is in the support of M infinity. But now that support is a union of irreducible components, so that tells us that any other point in that irreducible component is also in the support of M infinity. So that's how we will deduce that rho is also in the support of M infinity. And then you go down. Maybe I'll write this. Oh my God, sorry, yeah. That was the assumption. And then the conclusion is that rho is automorphic. Yeah. Or in other words, the corresponding map from R to E factors through T. Yeah, thank you. That's the end of the statement. And now I'll just give a quick sketch of a proof about how it follows from the proposition. So, like I said, R pi iota will give a point of spec R infinity in the support of M infinity. Because it's automorphic. So then the proposition tells us that the irreducible component passing through this point is also in the support of M infinity. So that's where you need a unique irreducible component. And then you can connect rho to rho pi iota along this irreducible component in the spectrum of R infinity. So then you win. At that point, you have to sort of take covariance to return to level 0. So that works out and shows that rho is automorphic. It's in. This implication? Yeah, so the support of M infinity is a union of irreducible components. That's what we said over here. And now I've got a point. So on a unique irreducible component, so that whole irreducible component is in the support of M infinity. The point is in the support of M infinity, so its irreducible component is in the support of M infinity. So now you can specialize to any other point on that component and get something in the support as well. Well, R infinity is not global. It's just a power series ring over a product of local deformation rings. So the components of R infinity are exactly in bijection with the product of components of the local deformation rings. Yeah, I'm suppressing some details, sorry, but yeah, that's the way it was worked. When we did this patching, we've done a sort of passage from global to local things. So R infinity is just a power series ring over a product of local deformation rings. Yeah. So then you're happy.
Yeah. But this does not apply to this.
It probably should. Yeah, but you have to check something. Maybe you want to know. You have to know local global compatibility to check that, because you have to check something about the local Gauss representation coming from pi. Okay, so that's a sort of example of an automorphy lifting theorem. So let me just give a couple of remarks about this, and then I'll finish. Okay, so continuing with this sort of idea, what can we do? Let's make some comments. So, well, maybe we can put ourselves in a situation where our local deformation rings are irreducible for all V in S. So in that case, the conditions in this theorem will be automatically satisfied. It's just one irreducible component everywhere. So everything matches up. And so in that case, you get full support, and you can deduce that R to T has nilpotent kernel. So that was our sort of original goal, you know, that was the target theorem. R to T has nilpotent kernel. If maybe your RVs aren't all irreducible, then you have to do something extra. So Patrick mentioned a little bit about the local deformation problems you introduce to do what's called Ihara avoidance. So that's where you do a sort of congruence between a deformation ring which is irreducible and one which is not irreducible. So that's one way to sort of get this R to T nilpotent kernel even without this assumption. The other sort of way is to use Wals's numerical criterion and variations of that. Right, so that's one thing. We just mention the sort of simplest possible case. That's where these deformation rings are actually all smooth. So they're formal power series rings. In that case, you can do a little bit more commutative algebra. You just use Auslander-Buchsbaum over R infinity, and you deduce that you have free R infinity modules everywhere, not just a module with full support. You get N infinity, a free R infinity module. Okay, and that's super good because now when you return to level 0, you sort of retain this freeness. And so in this case, you would have shown that the lowest degree homology, HQ0, is going to be free over the Hecker algebra. And the Hecker algebra is isomorphic to R. this is the sort of cleanest possible situation. If your local deformation rings are just power series rings, then you're super happy. You've sort of completely controlled. And I should say you can also control the higher degree homology groups. They're just sort of given by tors from M infinity, and you can sort of describe those as well. So this is a sort of very good situation where you get freeness over the hecagon. And again, so L0 can be positive in this situation, I think. Yeah. No, it's fine. We can talk about it later. Okay, let me just end. Sorry, I took some extra minutes without asking permission, but I'm going to finish right now. So let me just sort of illustrate what we sort of done up to now. We're giving you a slightly more concrete consequence of this kind of automorphy lifting machinery. So if you were Andrew Wiles and you'd done this kind of stuff in 1993, then where you would have got to is you'd have proved that it's something like if E is an elliptic curve over Q, good reduction at 3, semi-stable reduction elsewhere, I need some version of my enormous image condition. So that's going to say that the Galois action on the 3 torsion is absolutely irreducible. And then because we didn't do Ihara avoidance or this numerical criterion, we need an extra assumption to make sure we can check things about irreducible components. So the extra assumption is that, this mod 3 Galois representation should also be ramified at the bad reduction places for E. So if I assume those things, then using Langland's tunnel and the automorphy lifting theorem sort of that I've described here, you could get modularity of E. So the point of writing down this statement is, well, firstly, it's cool that we could prove some elliptic curves are modular, but secondly, you need to do quite a bit more if you want to prove modularity of all elliptic curves, in particular this sort of minimal ramification condition, but our residual representation has the same kind of amount of ramification as our three-adic representation. That's something that we need to eliminate with some other ideas. All right, that's it. Thanks very much.